Hello everyone, this is JFraire and this is my fifth test run for my audition for CNRS concourse. In this presentation, I will provide a quick overview of the context I'm developing my research in. I will highlight some of my main achievements and I will also introduce and present my research project. So, in the beginning of my career, after receiving my engineering degree, I've got involved in the industry, Motorola and Nokia Siemens Network Company for a little bit more than 3 years. And I've worked in terrestrial mobile networks in a team called New Product Introduction, which was basically responsible for developing new features, implementing them in mobile equipment and also in ground stations equipment from this company, and test them in the laboratory and also introduce them to the different customers around the world. But by the beginning of 2012, I started asking more fundamental questions about the technology, and not only just implementing existing standards, but also trying to. I was concerned about what were the reasons that drove these standards by then, and I started my PhD career with founding from the Argentine Space Agency and moved to the space terrestrial mobile networks domain, where I was trying to implement existing protocols in the space domain. Having worked in the industry for these years also allowed me to develop quite interesting industry and academy interaction during this period, and basically focus on and tackle and solve real problems during my PhD. And this also continued during my postdoc and during my researcher position that I currently have in the CONICET in Argentina. My research domain is space terrestrial mobile network, and if we take a look at what's happening today in this type of application, we generally tend to see this type of images where have too many satellites around the Earth and very big satellites as well, of several hundred kilos, in order to provide what's called an internet paradigm communication type, where a high amount of resources are used in order to sustain what's called a continuous connectivity from the source to the destination node in the network. But this type of paradigm, and this is something I questioned during my research, is not scalable and it's not resource efficient, and there is alternative solutions that can be used in this case for some type of applications, which is called store and forward paradigm, where nodes can basically store data temporarily in their local memory and forward them as communication opportunity becomes available, becomes discomposable because of energy or because the orbital dynamics of the networks. This type of network are also known as delayed tolerant networks. They are basically an adaptation of what happened in deep space networks, and they require of new models, algorithms, and protocols in order to implement in this network in space. In the end, DTN networks in low orbit, as we see here, are more resource efficient and open new possibilities for different space agencies and space industries as well. So in this context, one of my main scientific achievements was developing what's called contact plan design. This is a new research area I discovered while working in this research domain, and basically it has to do with explore how this turn and forward paradigm can cope with resource conflict or scarcity. As we do not have this constraint of having a continuous connection anymore, our nodes can basically store data temporarily. Then this temporary storage of data can be used to cope with resource problems. And this allows us basically to gracefully degrade the resources utilization and cope with different problems such as we see in this figure, such as limited energy on a given node, or also unavailability of a given node because of a failure or because of other type of scheduling problems that can be tackled by contact plan design. And in the end, what happens is that the overall topology of the networks, which is a time evolving topology in this case, can be basically reduced, and therefore the overall throughput of the network is reduced, but we can accommodate resource limitations such as we can see in this figure. What contact planning becomes in the end becomes what's called a satisfiability problem and eventually an optimization problem. So given a possible set of resource assignations in the network, then we want to ask it's a problem of whether there is any solution that satisfies this resource assignation, and if there is any, then we want to know which is the optimal one. So in order to answer this question, we need to develop efficient topology models. And we have studied during my research period different time-evolving and predictable for store and forward network models. One of these models is time-evolving graph, which is the one I'm showing in this figure, which basically captures the time evolution of the topology of the satellite networks in the x-axis, and for each moment in time, there is a state, there is a time interval where the topology behaves at a given the topology behavior can be represented by a given graph, and this is the connectivity of the network. And this is in this case, this is an example for satellites that gets together in the pole, and they have connectivity as they get close together, but as they fall apart, the connectivity stops happening. And then we have here in the color arrows, which will be a possible traffic flow assignation for this type of network, given that we have traffic from node 4, 3, 2 towards node 1. Another topology model we have studied is contact graphs, which are basically more suitable for routing, but in this case, for content planning, we have typically used time-evolving graph. Using time-evolving graph, we can then state different optimization problems. In this case, I will highlight traffic-aware contact planning, which is quite an interesting planning solutions where we assume that traffic is predictable, which is generally the case for space networks. Because we have a very good idea of what's going to happen in general, we know where our network is going to take a picture from in space, so we have a very good idea, so we can take advantage of this and state this type of modeling where we basically set variables such as the flow from one node to each other at any given state, the buffer at node at any given state, and also the resource assignation we're making to these nodes at any given state. And stating different constraints such as flow conservation constraints, link buffer and capacity and conservation, and interface and resources assignation constraint, as we can see here, we can finally state what can be like a variation of the well-known multi-commodity flow problem formulation, which is specifically focused in time-evolving store and forward networks in this case. And then we can state different optimization criteria, such as in this case, minimize the delivery time. Because we are delay tolerant, we can store data temporarily and we can deliver it with a high latency. But anyway, we want to optimize this and we want to reduce this latency, and this is what this model does. And this model basically delivers a contact plan, which can be then provisioned to the network, or it can be used on ground to calculate routes or to calculate routes on the network in a distributed manner. This is a very simple example of one of the case studies we had with the ACP. And this is 4 half-orbit networks. It's a very short time, but it still has we can have a very good idea of what happened with the model. The blue curve here, which is highlighted as non-resource constrained network, is the contact plan where the resources in nodes are infinite, and we have basically all the connections that are physically possible. And then the red curve here in these two graphs is the metric that we can get with TACP, basically with constrained resources. In this case, it's only we can have a single antenna enabled at any given time and at any node, and therefore both delivery time and the system contact time are penalized, obviously. So delivery time is a little bit higher with TACP, and the system contact time, which is basically a resource consumption metric, is better in the sense that we're having resource constraint, therefore we're using less resources in the network for all possible network loads. And we can see in this graph that TACP behaves better than most of the existing planning solutions that were existing by then. But TACP was just a cornerstone at the beginning for what was my research context. And from TACP, I arrived to TACP for different other contact plan design solutions, right? So this will be like here on the left side. And the problem with TACP by then was that the model becomes quite complex and it's very difficult to tackle large network. We're talking about maybe hundreds of nodes, and therefore we developed like heuristic approaches based on genetic algorithms. This is the EATACP, so we are seeing here in this graph. And basically, all these type of planning solutions eventually drove us to the routing domain, and we were able to make some quite interesting also contributions in the distributed routing algorithm. And these are also these are all the CGR variations. CGR stands for contact graph routing, and this is the state-of-the-art routing for this type of store and forward networks in space. These contributions eventually in routing, which are still happening today, were also allowed me to move to the performability domain, where we're trying to improve not only the routing metrics and the routing efficiency, but also the performance of the routing and also the fault tolerance of the routing solution. So this is basically my current research domain, and all these contributions allow me to make we have a book written on the delay-tolerant satellite networks summarizing all these contributions and the state of the art, book chapters, journals, and international conferences as well. But this doesn't only end in academic contributions, but also several application and implementations were developed during this period. One of the most important from my point of view is the Contact Plan Designer. Contact Plan Designer is an SDK2 plugin, which basically includes implementations of all the existing solutions for Contact Plan, and this involves linear programming model, as we have seen. This also involves like different algorithm solutions. This tool is currently spinning out. This is the one that we see now in the figure, and this tool is currently spinning out probably to a startup. It's currently having different users for this beta release, which is people from the University of Dresden, the University of Córdoba in Argentina, the Argentina Space Agency, and also some people from the Chinese Space Agency. Another contribution I would like to highlight is DTN-SIM. DTN-SIM is an event-driven simulator based on all the routing contributions we have made also, and this is an open source simulator which is also being used by several universities around the world at the moment. So we are also having quite interesting improvement from other people that are using DTN-SIM to solve and to answer questions about how the satellite network behave. Having a event-driven simulator is crucial in this type of network where we're trying to evaluate scenarios of several hours or several weeks, even weeks of duration. So DTN-SIM is having quite a strong impact in the community at the moment. And finally, I was like a collaborator in the Interplanetary Relay Network, which is a full protocol stack developed by JPL NASA. And I was able to develop different routing solutions which are currently being used in this protocol stack, which is at the moment being used in the International Space Station as well. So in this context, I was able, and also given my previous experience with industry, I was able to know how the industry moves, what's the language that the industry speaks, and I was able to develop like quite interesting cooperation between space agencies, between universities, and also within the industry. And this right obviously from Argentine Space Agency, the National University of Córdoba, and some companies, INVAP and STI back there in Argentina. But I'm also in continuous collaboration with JPL at the moment, and we're particularly in the interplanetary relay network software, and this is also in cooperation with the Johns Hopkins University. I'm deeply involved with the University of Saarland and the Technical University of Dresden, which both works quite closely with ESA. With different missions, and one of them is I'm going to describe next, which is one with GomSpace, which is a satellite hardware manufacturer from Denmark. We're developing different solutions for them as well. I visit the Chinese Space Agency almost every year to give a course of 1 month on the electronic satellite networks, and I also have ongoing project with Thales Alenia Space I will highlight next. And this cooperation network I built during this year allowed me to create what's called Extinct Workshop, I will also highlight later, and most importantly, have a deeply participation and collaboration with the IATF and CCSDS standardization committees, which are at the moment are standardizing what's called the bundle protocol, which is the default standard for delay tolerant and store and forward networking space. So ongoing projects I would like to highlight are the SARRE Constellation project, which is a project from the Argentine Space Agency being developed by this STI and INVAP companies. And this is a project which I'm currently participating in from the networking perspective, developing algorithms and solutions for routing in it's a store forward network as well. And most recently, I got involved with the Ullerik satellite constellation, which is from GomSpace. It's built by GomSpace for ESA and for the Denmark Space Agency. Have very similar problems. They're using CubeSats. This is a very small satellite we're seeing here in the picture. This is maybe like 20 centimeters per 40 centimeter satellites. These are quite small satellites. And also, I'm deeply involved with Thales Alenia Space in what's called S2P, S2V project, where they're trying to split very big satellites in smaller satellites and have the same performance of a big satellite with using several small nodes, which allows them to use smaller launchers and be more fault tolerant and so on. So this is another project I'm currently involved with at the moment. And this type of interaction with the industry and with different academy allowed me to create what's called the STEAM workshop. I'm the founder of this workshop, and this year is going for the fifth edition already. This is going to happen in Huntsville, Alabama, and STEAM workshop has been held around the world for 4 years already. With very interesting community. We are a small community. We're no more than 50 or 60 people working on this, but it's still a very strong. It has a very strong and committed and promising future. So in this context, I would like to present what's my research project. My research project has to do with the idea that space terrestrial mobile network, which is my current research domain, I have brought a lot of solution from space network, from this space network, which is basically DTN. Storm forward in space networks and in deep space network is the only possible solution. And this is not true in low orbit, where I'm focused at the moment, where not only storm forward is possible, but also internet is possible. But I found here that in low orbit that I'm still having quite a good reasons to use storm forward because of the resource efficiency. And my theory is that if I keep going to the terrestrial networks with this paradigm, then I may have some quite interesting results as well. My hypothesis is that what's today known as Internet of Things or IoT is quite not correctly named, in the sense that we might not need to use, or we might not want to use internet as a solution for connecting things. We might want to use a different approach, which is in this case DTN, storm forward, and we are talking about things that have very low resources, that have like sporadic connections, opportunistic connection, where having a continuous connection like internet is built to sustain, might be just impossible to do. So this is my hypothesis. And what I'm planning to do in my research project is to move from this space and space terrestrial network to the terrestrial domain, and therefore moving all this performability analysis we have been making for space and try to apply this to the terrestrial networks, where obviously we understand performability by the mixture of performance and fault tolerance. This is been my main research axis, and this axis I propose to move this toward the terrestrial network. And in the other hand, applying scalability features from terrestrial network, which are widely developed for thousands and millions of objects connected, and applied also this theory as a secondary research axis that moves from the things in Earth to the things on space, and in order to foresee how space is going to scale in the future. So I have highlighted some short-term objectives in my research plan, such as routing parallelization in space and route table lookup and fault recovery, which are mostly aspect to works on the space domain. And as we move to the terrestrial network domain, then I believe that studying about how routing scalability can be assessed from when routing, I mean with routing that are built for storm and forward routing in space, move this to Earth. How does that can scale in the Internet of Things domain, and also using banding heuristics and scalable routing framework and so on to mix these two domains and basically obtain a unifying paradigm for what I call challenger networks, which happens in this space, happens in low orbit, and will also happen in the Internet of Things domain today. So this project quite nicely integrates with current LAS LAS laboratory, and particularly with the SARA team. And the currently SARA team is formed by different research axes. We're talking about network analysis and optimization, where basically different model and theory happen, networking model and theory is happening. Also, network and service architecture focused on Internet of Things and machine-to-machine communications, and also different axes which are networking protocol, where software-defined network and satellite networks are the main research topic. And interestingly, my research profile and my research project it tackles these three areas at the same time. So I believe that continuing my research project in the LAS laboratory can be quite promising, because I will be able to integrate the three research domains in the CNRS laboratory. Other laboratories, such as the ERIT laboratory, has also showed some quite good interest in my project, and I still believe the ERIT is a good alternative host laboratory, in the sense that it's still based in Toulouse, and I believe in Toulouse is a key city to develop this project because of its aerospace trajectory, and all the aerospace company and CNRS and ONERA and the different space agencies working there. So I believe Toulouse is a good place to go for this project. And also the LIRM laboratory has shown some interest in, however, only on the research and radiation team on the hardening part of my research project. So this is all. I would like just to thank you for your time. I would like to thank Nicola and Pascal for the feedback. And well, I'm almost reaching my 20 minutes duration. So if you have any questions or discussion, I have some backup slides I could share with you. So in particularly, I plan to prepare a few backup slides in order to answer this question and provide some further information on these topics, just in case there are some specific questions. Thank you.